Okay, so now let's look at some properties of composition of functions. So what I really want to do is to look at my basic properties, things like increasing, decreasing, bounded, even, odd, and think about what happens when I compose functions with those properties. Is there much I can say? So let's start off with f and g increasing, shall we? Then this guarantees the composite is increasing. That's quite nice. So the composition of increasing functions is increasing. Let me show you why this is true. So let's give ourselves a little bit of space. This is a little bit too pushed up. So what does increasing mean? Increasing means it preserves inequalities. So if I was to take, let's say, a less than b, I need to show that when I feed both of these into the composition, the inequality stays in the same direction. Now, I'm assuming it's true of g, for example. So that is literally the statement that g is increasing. Kind of a really nice, crisp way of talking about it. But then f is increasing. So that means what? Well, if I feed these into f, the same thing has to hold. And that is literally the statement. I mean, that f composed with g, a, is strictly less than f composed with g evaluated at b. So by definition, f composed with g is increasing. So I've already proven it more than anything else. This is an actual reason it's true. So, warning. This is not true for decreasing. Which is agony. It feels like it should be so obviously true for increasing, if it's true for decreasing. It doesn't work, actually. So, warning. And what I mean is decreasing does not imply the composite is decreasing. It actually implies it's increasing. But I don't want to get bogged down with too many weird examples. So this is not true for decreasing. Not true for decreasing. Or some combination of increasing and decreasing. So what I mean by that is you could have a function which is increasing some of the time, decreasing at other points. If you're doing composites of those, it's a free-for-all. Anything could happen. So shall we do an example? Two decreasing functions. So two decreasing functions. Where are we? So let's do f of x is minus x. That's decreasing. And we'll do g of x. G of x is equal to minus x cubed. These are both decreasing. And what's the composite? Well, let's just think this through very carefully. So f, so what am I doing? So f composed with g of x, what's it equal to? It would be equal to, so it's f of gx. Okay, so that's equal to what? That's equal to f minus x cubed. But now that's just equal to minus of minus x cubed. This is equal to x cubed on its own without the minus. And this actually is an increasing function. So the composite of two decreasing is not decreasing. Okay. more than anything, as I said before, with these properties, they're quite fiddly. You don't want to memorize these, but you want to kind of understand the logic that goes into them, right? Because that's where your true understanding is going to come. Understanding kind of the finer details of what I'm describing here is really the key to success here. Okay, let's do bounded. So these are interesting. So it turns out that if f is bounded, this guarantees the composite is bounded. It doesn't really matter what g is. Now the reason for that is because ultimately the output of the function is f of something. It's f of gx, sure, but gx is just a number. So if f is bounded, that value can't be bigger than something. So for example, if I was to have f of x bounded above and below by 5, so I could write it like that, well, this guarantees this. Is strictly less than 5. Why? Because gx is just a number. So it's just f of a number, and sure, we're writing it in a slightly strange way, but still works. So it's important to understand that this doesn't work the other way around. So warning. Warning. I suppose if g is bounded, this does not imply that the composite is bounded. Okay? So the inner one is bounded, it makes no difference at all. So let's do kind of an example we saw before with quotients that messed everything up. So let's do f of x is equal to 1 over x, and let's do g of x is equal to x squared. And let's restrict these. Restricted to the interval, open interval 0 to 1. So I'm going to restrict the domain. Well, first of all, g is bounded. Right, it's bounded by 0 and 1 actually, right? Can't get bigger than 1, can't get less than 0. Squaring keeps you in that interval. F is not bounded though, no way, because as x gets closer to 0, 1 over x is going to get very big positive without any upper bound. So let's see if that messes things up. But if I do the composite, what's this equal to? So the composite is f composed with, or f with the input replaces x squared, and this is 1 over x squared. Same logic as 1 over x. Same logic as 1 over x. This thing is unbounded. Unbounded. So just because the inner one was unbounded, it doesn't tell you anything about the outer one. So unbounded as 1 over x squared kind of grows positively. Without bound. Without bound. As x gets closer to 0. As x gets closer to 0. Maybe just a picture to help you with this. This is what the graph looks like roughly. If you were to graph this, as you're going to see in later videos, it looks kind of like this. So I'm going to graph the entire thing. It looks kind of like this. So you can see there, as you get closer and closer into 0, it's getting bigger and bigger and bigger. So there's no horizontal line that traps it. It can get as big as it wants as I'm willing to get closer into 0. So interesting. This example, bounded the outer function matters, the inner one function doesn't matter so much. And there are all sorts of weird and wonderful things that can happen, but these is kind of some good stuff to be aware of. So let's think about symmetry now, shall we? So symmetry, odds, evens, all that kind of business. Let's have a careful think about this. So this again isn't so easy. You've got to think really carefully about it. It turns out the following is true. These aren't completely obvious. If G is even, that guarantees that the composite is even. Now why is this true? Well, let's just do an example. Let's take gx is equal to x squared. Now, apparently this is true regardless of what f is. So let's see if we can check it. So remember what we need to do. To check even, you need to feed in minus x and see it's equal to x, or it's equal to the output of x. So f composed with g of x. In fact, let's do minus x first. Makes more sense generally when we're doing this. What's this equal to? This is equal to f composed with g of minus x. Yeah, so that's the meaning of the composite. But now g is even. So this is f of g of x. A little more space. G is even. So g of minus x is equal to g of x. That's the meaning of being even, remember. But now this is just what? Well, by definition, this is the composite function evaluated at x. So I've just checked that minus x and x give the same output. So this is exactly the statement that f composed with g. In fact, maybe make myself, I'm doing a general proof here. I should really have done this just with x squared. So really, I don't need this. So this guy is an even function. We've checked the defining property. So with all this kind of thing, you need to really understand the definition of what even is. I'm feeding in minus x because that's what matters when it comes to checking if something is even or odd. So let's do another one. Her warning. I think it's a good place. F even does not guarantee that the composite is even. Absolutely not, right? So that's kind of weird. It's only one way around. So let me just show you why. Let's do it by example. If I do f of x is x squared, so I will do an example here. And let's do g of x is equal to x plus 1, shall we say. So this implies what? This implies that f composed with g evaluated at x, what's it equal to? It's f with g of x fed into it. That's equal to f with x plus 1 fed into it. That's equal to x plus 1 all squared. Now let's factor this out. This is x squared plus 2x plus 1. Is this an odd or an even function? Well, no. It's a polynomial and it has exponents which are both even and odd. So this is kind of a shortcut for spotting, and it's only a shortcut for polynomials. If you have a polynomial, it's even if and only if all the exponents are even numbers, and it's odd if and only if all the exponents are odd numbers. And we've got a combination here because x is x to the power 1. So this is neither odd nor even, but it's certainly not even. So this is neither odd nor even. So really these are just quite good exercises in understanding what odd and even means, or at least checking. So I'll do two more just for a bit more practice. So if I have the following, so if there is a little bit of a fix here. So if f is even and g is odd, this does guarantee the composite is even. Pretty wild, eh? So let's check why this is true. Let's do it by example again. Let's do f of x is equal to x squared, and let's do g of x is equal to x cubed. So super simple. So f composed with g of x is equal to what? It's f with g of x fed into it. That's equal to what? F with x cubed. But now this is x squared, isn't it? So this is x cubed all squared. That's x to the 6. And now that's an even function, because there's only one even power. But remember, to check this carefully, you'd have to feed in minus x and to see it was equal to x. So this is an even function. So it's a good exercise to try and show this in general. It'll be something incredibly similar to what I did here. It's basically identical to this procedure. You feed in minus x into your composite and just go through carefully what everything means. Okay, one last one. What about if I'm composing two odds? Composing two odd functions, what does that do? This actually guarantees the composite is odd. So let's do a pretty tricky example here. Let me think. So if I did f of x is equal to x cubed, it's definitely odd. And let's do another more interesting odd function. Let's do f of x is equal to x times the absolute value of x. Now, I think most people, when they look at this, they'll be like, oh God, is that odd or even? What's going on? Now, I suppose if we're going to be fancy about it, we do know that x is odd and the absolute value of x is even, and the product of an odd and an even is odd. But let's just check this quite carefully. So g of minus x would be equal to minus x multiplied by the absolute value of minus x. That's just minus x times the absolute value of x, which is equal to minus g of x. Okay, so this implies that g is odd. So we checked it from first principles, right? We saw that if I feed in minus x, I get minus of the output if I feed in x. So what happens when I compose now? So let's see this. Okay, this one's a tough one. So it's f composed with gx. So we've got to be very slow here. This is f. What's gx equal to? It's x times the absolute value of x. So now what's this equal to? Well, f is cubing, so this is just going to be x times the absolute value of x, all cubed. So I suppose this comes out to be equal to x cubed times the absolute value of x, all cubed. And at this point, it's a nice exercise to check that it's actually odd. What is again true is this is odd and this is even, because the absolute value is even, remember? And the product between odd and even is odd. So overall, this guy is an odd function. It's a pretty difficult example, but I wanted to do one that was a bit less standard, just so you get a bit more practice in composing things.